Last class we discussed about what do you mean by a CST element. So CST is what we call it as a constant strain triangular element. And we also identified the way to convert a three-dimensional object to a two-dimensional object, right? So we can categorize into three different types. So one, we call it as a plane stress problem. So one, we call it as a plane stress problem. So when you call this as a plane stress, when your stress in Z directions are zero, right? So we call that as a plane stress problem. It is usually applicable for thin elements or when the thickness is lesser, right? Then we can consider that problem as a plane stress. Next, we can categorize that as a plane strain problem. So as the name indicates, strain in your Z directions are zero. So this is applicable when you have very large thickness, right? When your Z axis is very large when compared to your X and Y axis. The third one, so we call it as an axisymmetric problem. So when you say axisymmetric, it is a cylindrical object, right, which is converted as a rectangle so that you can concentrate only on a rectangular path. You can analyze it. So that will be considered as a whole cylinder, right? So these are three different way of converting your three-dimensional object to a two-dimensional objects, right? So then we started to derive what is your stiffness matrix. And when you identify, we got two different matrices. So one is this B matrix. So whenever I say it's a B matrix, it is relation between strain and displacement. So relation between strain and displacement, that we call it as a B matrix. You also have another matrix which is D matrix. So which is material property matrix or stress strain relation matrix. It is stress strain relation matrix, right? So these are the things we are going to identify. And we also find, so last class we also discussed your interpolation functions, what is N1, N2, N3, right? So where N1 we call it as P1 plus Q1x plus R1y divided by 2a, right? This is what we consider. Similarly, we also identify for N2 and N3. And P1, P2, so P1, P2, P3, Q1, Q2, Q3, this also has a separate formula, right? So this is what we discussed. Now we'll proceed with what is the how to derive a strain displacement matrix. Okay. Before that, I want to discuss what is the main importance of this N1, N2, and N3. So that is your interpolation functions. Let me consider. So let me consider this is my element. So this triangular element is having three nodal points. Nodal point 1. So which is having displacements U1 and V1. So U1 is your X displacement and V1 is my Y displacement. Similarly, nodal point 2, which is having U2, V2, and nodal point 3, which is having U3 and V3. So the purpose of this interpolation function is, if I want to identify what is the displacement at this point, assume that you have some displacements, right? So U1 is displaced to 0.6 mm. Let me assume. U2 is displaced to 0.8 mm. U3 is displaced to 1.2 mm. Similarly, V1 is displaced to around 0.1 mm. Some values, right? So some values related to that. So this is displayed to minus 1.3, 1.2 mm. And this is displayed to some other, so 1.5 mm, something like this, right? So I can identify what is this values of this U1, V1, U2, V2, U3, V3 by using our regular stiffness matrix formula. So by using F is equal to, by using F is equal to K into U. So we can apply the boundary condition, then we will identify what is this U1, U2, U3, and based on that we can identify these values. But what happens? I want a value in between this particular triangle. So somewhere at this point x comma y, right? Somewhere along this inside the point of this xy. In that case, so to identify that, we are applying this interpolation function, right? So what will be your x value? So the displacement at this, let me consider this u. You know these values of u1, u2, u3, v1, v2, v3, which is mentioned, right? We can substitute that things. Okay, that is okay. Now, how to identify this n1, n2, n3, right? So how to identify this n1, n2, n3? So this is dealing with these coordinate points. So you know this one will be like x1 comma y1, and this is equal to x2 comma y2, and this 3 is x3 comma y3, right? And we already derived the formula. So n1 is equal to p1 plus q1x plus r1y divided by 2a. So a is the area of this triangle. P1, what is P1? So let's consider as xy minus xy. So 1 is in clockwise. So for example, P1, if I want P1, so P1 will be like x2, y3 and x3, y2. So this is my P1. I will tell you how I got these things, right? We will discuss it later. So similarly, Q1 will be like y2 minus y3, right? And r1 will be equal to x3 minus x2. You have that formula, you can apply that, and you can identify these values of n1, n2, n3, right? So this values is used to find out what is the value in between your triangle, inside your element, right? That is the main purpose of finding out this n1, n2, and n3, right? So now, okay, these are the main benefit of finding these values. Now we'll go for deriving what is the stiffness matrix. What is the strain displacement matrix? Sorry, what is strain displacement matrix, right? So let me consider your displacement function u as n1 u1, n2 u2, n3 u3. Similarly, v as n1 v1, n2 v2, and n3 v3. So when I write it in the matrix form, we can write it like this. So U is displacement along x direction and displacement along y direction, which can be written as n1 0, n2 0, n3 0, and 0 n1 0 n2 0 n3, right? Which you can writing like this, right? So when you multiply, you will get the same things. So whatever I am mentioning here, that will be written in a matrix form. Okay. So now, what is strain? So strain along your x-axis is du by dx, right? So that is the formula, right? So we also call this dou u by dou x, so partially integrating it, sorry, partially differentiating this, right? Similarly, strain in y direction will be dou v by dou y. Shear strain will be dou u by dou y plus dou v by dou x. So this is the mathematical relation for your strain. So we are going to apply it in this equation. So we are going to apply these things in this equation. So what do? I need what is my values with respect to dou u by dou x, dou v by dou y, and similar to that. So in that case, what I have to do? I have to integrate it. So sorry, I'm going to differentiate it. Okay. So this I am writing in a matrix form. So your strain Ex is dou u by dou x, Ey is dou u by dou y, and your shear strain is dou u by dou y plus dou v by dou x, right? So this dou u by dou x, if I identify, it is nothing but, so u is, you know, it is n1 u1 plus n2 u2 plus n3 u3, right? So which I can write as dou n1 by dou x u1 plus dou n2 by dou x u2 plus dou n3 by dou x u3. So we are writing like this. So this similarly for v, I can also write it like that. And dou u by dou y plus dou v by dou. So this is for shear strain. We can write it like this. So now our aim is to identify what is dou n by dou x, right? Let's identify. So when we write it in a matrix form, how would it be? It is like dou n by dou x 0, dou n2 by dou x 0, dou n3 by dou x 0. So writing similar to that. Okay. So this, when you take, so you know what is the values of this n1, n2, and n3. So you know that it is p1 plus q1x plus r1y divided by 2a. So similar to that. So now in differentiating these things, so n1 differentiating it, what I'll get? I'll get just q1 by 2a. n2 differentiating with respect to x, q2 by 2a. Differentiating with respect to x again, n3, q3 by 2a. So differentiating y, r1 by 2a, r2 by 2a, and r3 by 2a. Right? You can substitute these things. In this matrix. Right? Everything is in terms of dou n by dou x or dou n by dou y. Okay. So when you substitute, I'll get something like this. 1 by 2a is a common term. q1 0, q2 0, q3 0, 0 r1, 0 r2, 0 r3. Just cross multiplying this. So r1 q1, r2 q2, r3 q3. This is my overall matrix. The first row indicates strain in x direction. Second row indicates strain in y direction. And third row indicates your shear strain. What is the shear strain? Okay. So the strain displacement relation, it is strain is B into du. So what is B? D by dx. Okay. So what is my B matrix? So in this case, when I relate this is my strain. This is my B matrix, right? This is my B matrix, and this is my displacement. So in that case, your B matrix is 1 by 2a, q1 0, q2 0, q3 0, 0 r1, 0 r2, 0 r3, and r1 q1, r2 q2, r3 q3. Right? This is my B matrix. So this is the relation between strain and displacement. So for a CST element. Okay, right. So to identify our stiffness matrix, we know that it is B transpose D B into area into thickness. This is the formula. So we identify B matrix. Okay. Now the next step is we have to identify what is my D matrix. Right. So D matrix is stress strain relation matrix. Okay. Previously is a 1D. I can directly written as E, Young's modulus. But here it is different. Okay. So Young's modulus in x direction, y direction, and xy direction. So you have to identify something related to that. Okay. We proceed. So what is the values of this Q1, Q2, Q3, QR1, R2, R3? Right? Sorry, I forgot to mention this. So this Q1 is Y2, Y3, Y. So how to identify this? How to remember these things? That so easily. So let me consider this is my triangle, right? Which is having nodal points like this. Nodal point 1, which is x1, y1. Nodal point 2, which is x2, y2, and nodal point 3, which is x3, y3. Right? So the easy way to remember these formulas, right? So one step is you can consider either clockwise or anti-clockwise. That's it. So your Q1, right? Your Q1, let me consider it is rotating in anti-clockwise direction. Your R1, consider it is rotating in clockwise direction. Okay, just for remembrance. So if I want Q1, right, always consider Q is related with Y. Q is always related to Y. So this is my point 1. So when I move in clockwise, so anti-clockwise, the next point what you are getting is 2 and then 3. So Y2 minus Y3. Okay. For example, if I want Q2, right, move in anti-clockwise, so y3 minus y1. So first 3, then 1. So if I want Q3, move in anti-clockwise, y1 minus y2, right? That is what you can remember this. Similarly, to remember this R, you can also consider the same. R in clockwise, or you can consider minus of anti-clockwise, whatever it is required, whichever is convenient for you. So if it is 1, if it is confusing you, you put minus of anti-clockwise, right? So it is up to you. So 1, so I'm going to move in clockwise. So R relates with X. So always whenever you see R, you have to consider with respect to X. So first point is 3, second is 2. So X3 minus X2. If I want R2, move in clockwise, X1 minus X3, right? If I want R3, move in clockwise, it is X2 minus X1. Stress strain relation matrix. This matrix, you have 3 names for this: stress strain relation matrix, constitutive matrix, or material property matrix. All are same. Material property matrix, right? So everything is same. So it indicates D matrix, right? For this, remember what you have done in strength of material. Same thing. I'm going to take a figure, object which is having stress in X, Y, and Z direction, all the 3 directions, right? So let us identify what is the strain in X, Y, and Z directions. You know that one side you will have a longitudinal strain, other 2 sides you will have a lateral strains. So you know the relation between longitudinal and lateral strain. So lateral strain you can write it as minus mu into longitudinal strain, right? So that I am writing it here. So Ex, I can write it as longitudinal strain in X direction, which is sigma X by E, minus mu into sigma Y by E, minus mu into sigma Z by E, right? So this is my strain in X direction. Strain in Y direction, minus mu, similar to that, strain in Z direction. So I think these things we discussed in our strength of material class. Same thing. So strains in all the 3 directions, I am considering it. Now what I can do, I have a relation here. Let me identify, right, what is my plane stress condition. So I'm going to solve it for plane stress condition. So your material property matrix, D matrix, can be categorized into 2. One, what is for plane stress condition. Other is for what is for plane strain condition, right? This is the difference. Your B matrix will be same. Only your D matrix will be different, right? So let us consider plane stress condition. For plane stress condition, your normal stresses in Z directions are zeros. In that case, your sigma X, tau XY, sorry, XZ and tau YZ. So all are zeros. In that case, what I can do, this is my equation. In this, I will put sigma X and sigma Y. So these things are zeros, right? So what happens? This becomes 0. This becomes 0. Right? So you will get something like Ex is this and Ey. So your strain will be like this. Okay. Similarly, tau also we can identify. So these are, so tau we can relate it in different way. Okay. So this is, let me consider this 2 as equation to identify what is the values of this sigma X and sigma Y. So what I will get is sigma X when I solve this 2, equation 4 and equation 5. I'll get sigma X is equal to E by 1 minus mu square. This is mu. Okay. So Poisson's ratio mu. So mu square. So Ex plus mu Ey. Okay. This is also Poisson's ratio. Okay. So similarly, sigma Y, we'll get another term. Okay. So considering solving these 2. So now what I can do, I have a relation. So tau, I can write as G into this, right? So what is this? Shear stress shear stress by shear strain. You know that shear stress by shear strain is modulus of rigidity, right? Or shear modulus. So this is modulus of rigidity, which is G. Okay. So we are relating that. So tau, so this shear stress is equal to modulus of rigidity into shear strain. So this modulus of rigidity, I can write it in terms of E, right? You know the relation, right? So your E is equal to 2C of 1 plus mu. I'm applying that, I'll get an equation. Okay, what is the stress in terms of strain? Now what I can do, I have all this stress, so all this stress in X direction, Y direction, and Z direction, but your shear stress in Z directions are 0, which means I can cancel this two. No need to worry, right? I can concentrate only on this part. Okay, so now I can write this all these things as an equation, right? So just think about it here. In previous step, the common term what we have is this E into 1 minus mu square. This is my common term. You can able to see here. So here also, so for sigma x and sigma y, in both the cases, my common term is this E into 1 minus mu square. But when you go here, when you identify here, it is 1 plus mu. It is not, you can't able to merge this matrix. So because it is not having any common term here, right? So in order to make that as a common term, what I'm do, I'm going to multiply and divide by 1 minus mu, right? I'm multiplying 1 minus mu and dividing by 1 minus mu. So that is one term. When I do that, what I'll get? I'll get this as 1 minus mu square. Now this is a common term now, which is also relating with your sigma x and sigma y, right? So what are the remaining part that I can put it in the matrix? So when I do that, so when you do all these things, I put it in the matrix. So this is my matrix: E by 1 minus mu square, 1 mu 0 mu 1 0 0 0 1 minus mu by 2, right? So this is my D matrix, right? So stress strain relation matrix for plane stress condition. This is for plane stress condition, not for plane strain condition. Okay, only for plane stress condition, right? So this also you have to remember. So this set of formula. Okay, right. So now let us go for plane strain condition. So how to identify D matrix for a plane strain condition? So you have the same equations, right, which you already discussed. I am writing all this equation in a matrix form, right? So after, so see, in all these things, strain is in this side and stress is on the other side. When you equate all these three, I can able to identify what is sigma x, sigma y, and sigma z. So I'm identifying that, we will identify that things, then write it in an equation. Okay, so you will get overall equation like this. Okay, no need to worry about it. So just look after, that's it. No need to think this. Let us consider it. So you have sigma x, sigma y, sigma z, tau x y, tau y z, and tau x z. So these are the overall matrix, right? Strain displacement matrix for in 3D. So this is for 3-dimension, right? If you have 3-dimensional element, then this is my matrix. Okay, so now for strain, plane strain condition, you know that strain in Z directions and strain in all these Z directions are 0. Okay, in that case, so this is 0, this 2 is also 0. So what I can do, I can eliminate that rows and columns. Okay, I can eliminate that particular rows and columns accordingly. Okay, so what are the remaining term? That is my matrix. So this is my D matrix. Right? This is my D matrix for a plane strain condition. Okay. So you see the difference. So D matrix for plane stress condition. What is that? It is E by, right? So whereas for plane, this is for plane stress condition. This is plane strain condition, right? This is for plane strain condition. Okay. So you can see the difference. So you have a difference in your E values, and you also do have a difference in the diagonal. Okay. So other things are same. So based on your problem, you have to consider the D matrix, right? So only this will be different. Okay. So stiffness matrix, you know that your stiffness is integral B transpose dB into dV. So we will write it. So your stiffness matrix will be B transpose dB into A into T. Volume I can write it as cross section area into thickness. So area into thickness, not cross section area. So area of the triangle. So where area of the triangle is half into 1 x1 y1, 1 x2 y2, and 1 x3 y3. So these are my conditions. So this particular slide shows you all the formulas, right? So now we will proceed with a few problems, simple problems. Let us start with interpolation function. We consider the first problem. So this problem is related with interpolation function or a shape function. Okay. So let me consider you have a triangle with nodal points. So 1, 2, 3, and they are given what is your values of these nodal points. So 2, 3, all these things. Okay. They're asking what is your shape function based on the point P, which is 3.5, 5. Right. You have a point P here. Right. You have a point P here, which is 3.5, 5. Okay. Based on this point, you have to identify what is N1, N2, and N3. Okay. Note that. So the properties of interpolation function is same what we discussed in your bar element. Okay. What is that? So your shape function is always lesser than 1, and addition of all the shape functions n1, n2, and n3, when you add it, you will get 1. So this is lesser than or equal to 1, and the addition of all these shape function will always be equal to 1. Okay, these are the two conditions. Okay, what you want to do, let us consider. So for this problem, we have x1, x2, x3, similarly y1, y2, y3, all the values. We are writing it accordingly. Now, to find what is the shape function for the point 3.5, 5. So let us write the formula. What is my formula? So you know n1 plus n2 plus n3 is equal to 1. This is my first condition. Second one, any location x that can be identified as n1 x1 plus n2 x2 plus n3 x3. Any location y that can be identified as n1 y1 plus n2 y2 and n3 y3. Okay. So what do I do? Just substitute it. That's it. So n1 plus n2 plus n3 is equal to 1. X is 3.5. So that is equal to x1 is 2, x2 is 7, and x3 is 4. So 2x1, 2n1 plus 7n2 plus 4n3. Similarly, y, so y is pi, is equal to 3n1 plus 4n2 plus 7n3. So just substitute these values. So you have three equations, three unknowns. Solve these three, you'll get the values of n1, n2, and n3. Right? So for verification, if you add this, it has to be 1. It has to be 1 approximately. Let me consider at nodal point 1, you have 50-degree temperature. At nodal point 2, I have 100 degrees centigrade temperature. And at nodal point 3, let me have 150 degrees centigrade temperature. Now, my question is, what will be the temperature at point P? What is the temperature at point P? So this is my overall structure. You have temperatures at each nodal points. I have to identify what is the temperature in between, right? So what can we do? We use the interpolation function, right? So as like x is equal to n1 x1 plus n2 x2 plus n3 x3. Similarly, y is equal to n1 y1 plus n2 y2 plus n3 y3. I can also put like T is equal to n1 t1 plus n2 t2 plus n3 t3. Right? What is T? That is what I am going to identify. What is n1? We already identified. It is 0.4166 into T1, temperature at nodal point 1, which is 50 degree, plus n2, 0.1111 into temperature at nodal point 2 is 100 degree, plus n3, which is 0.4723. Temperature at nodal point 3 is 150 degree. So what is the value of T? Can you solve and tell me? 102.785 degrees centigrade. Hope you can understand how to identify the temperature. This is how you can able to get the temperatures at any locations, right? At any locations of your particular problem. So now we'll go for another problem, same type. So related to that, but a little bit difference. So what they given here is the interior point P x coordinate is given, which is 3.5. N1 is given 0.4. They are asking you to calculate what is N2, N3 and coordinate point Y. Same procedure. So what are the given data? I am writing all the given data. So you know what is X1, X2, X3. So these are my X1, X2 and X3. And you know what is Y1, Y2, Y3. We are writing in that. Then I also know what is X, which is 3.5. And also I know what is my N1, which is 0.4. Same, you use the relation. N1 plus N2 plus N3 is equal to 1. X is N1, X1 plus N2, X2 plus N3, X3, and Y is same. Substitute all these things, right? You'll get the equation. So of course, here also you have three unknown data and three equations. You can solve these three equations. You will get the values of N1, N2. Substitute that, you will get the values of Y. This is one type of problem related to CST element, right? So we will solve other problems in next class.